1, go. Hello and welcome back to Calculus 2. We are ready to wrap up this course with chapter 12. We have 3 sections left. The first of those 3 is the section on parametric equations. So this is setting up our Calculus 3. Parametric equations are really cool creatures. We'll see what they do, and we'll switch to polar coordinates. So parametric equations are sets of equations where we use a common parameter which allows us to disassemble and break up dimensions so that each dimension has its own equation. I'll give you an example immediately. Say you have a circle x squared plus y squared equals to 9. Set of parametric equations that describes this particular circle is x equals 3 cosine t and y equals 3 sine t, and this t is in between 0 and 2 pi. What you see here in this red box are parametric equations. For circle radius 3, because we know 3 squared is 9 on the other side, right? Now, for circle and ellipse, you memorize these. For the other ones, you can actually find them. So what are the features over here? Well, note that dimension x is separate from dimension y, and the only thing they have in common is this parameter t. You can think of t as time, and x and y, you can think of those as dimensions of length, which is the distance, and you are covering x amount of distance in time and the y amount of distance in time. So you can think of it that way. Now this parameter t, you can put an s, you can put a theta, you can put whatever you want to call it. It's just an extra parameter. Once you have set of parametric equations, you can combine them together to get the type of the equation that you are used to. So we can combine parametric equations to eliminate parameter and get equation we are used to. So if I have x equals 3 cosine t and y equals 3 sine t, what I can do is I can go here and say cosine t is x over 3, from where t is equal to inverse cosine of x over 3, and I can plug that in. This eliminated parameter, and now I have y equals 3 sine of inverse cosine x over 3. Now you should recognize this problem all the way back in trig. You had a whole bunch of these to solve for homework, and no one ever told you why. Patience, right? Patience, young Padawans. There you go. That's the reason why you did those ridiculous problems that had no context, nothing to it, right? You shoveled those triangles around, and now all of a sudden they are useful. And those problems are going to be useful in your trig sub, they're useful here, and they will be useful in differential equations again. You haven't seen them anywhere in Calc 1, so, right, a little bit of patience pays off. So all I need to do is to simplify this, the sine of inverse cosine, and then we're done. Well, if you remember that when you compose function with its inverse, you should get x back. So my goal is to change cosine inverse into sine inverse, and then when I cancel those two out, I will just have the argument of whatever that sine inverse had. So to that effect, I have to, well, let's draw the triangle here, put a theta in there, and cosine is adjacent over hypotenuse, which makes this side 9 minus x squared if you use Pythagorean theorem. So now you will write sine instead of cosine. So cosine is x over 3. Sine will be square root of 9 minus x squared over 3 because it's opposite over hypotenuse. At this point, sines canceled. We have y equals 3 times square root of 9 minus x squared over 3. Now 3 is canceled. And we get y equals square root of 9 minus x squared. Square both sides, that's y squared is equal to 9 minus x squared. And move x squared to the other side to get the equation for the circle. So we just showed that those two parametric equations combined, right, will give you equation of the circle if you put it. So now you can write the circle here in blood. You can write the circle as x squared plus y squared equals to radius squared. Or you can write the circle as x equal r cosine t and y equal r sine t, where this t is between 0 and 2 pi. Now some of you would be looking at this and going, why? Why would I want, instead of one equation over here, there, two equations plus that condition? How's that easier? Well, hold on. Is this a function? No. How about each individual one over here? Ah. Okay, now we see the benefit. See, parametric equations are going to give you functions on the other end, where the equation you have on the left, circle, not a function. Ellipse, not a function. Sideways parabola, x equals y squared, not a function. All of those transferred to parametric equation give you sets of functions. So there is a huge benefit there. Huge benefit. So circle is given as that. What else is cool? Ellipse. Ellipse is cool because you have your x squared over a squared plus y squared over b squared equals to 1. Ellipse is a more general circle. Circle is a special case of ellipse. You see, if your a equals b, then it becomes, you can call it, if a is equal to b and you call it r, then it becomes r squared in denominator. And then when you move it to the other side, it just becomes x squared plus y squared equal r squared. So every ellipse is a circle if a is equal to b. We have a parametric set where x is equal to a cosine t and y equals b sine t. T between 0 and 2 pi. There's your parametric set for an ellipse. It has a and b, right, which are the made a little bit better. This is your a and this is your b. And if a is equal to b, then obviously you have a circle, which you can show by replacing a and b with r and then just working out the algebra. Parabola. And I'm interested mainly in the sideways parabola because we know that the regular parabola y equal x squared is a function, so we're all cool there. No issues. It's the sideways one that I like to think about, right? Because the sideways parabola, like this, is not a function, right? If you draw sideways parabola like this, you see it's not a function. So obviously you can't integrate, you can't do a lot of calculus stuff because it's not a function. Now, parametric equations have a nice way of dealing with this. You need to have an equation for x, and you need to have an equation for y. Now, the quick hack method here is to say, well, let y be a t and x to be t squared, right? So if you have it this way, hey, it just became two polynomials, right? You have like a y equal x linear line going through the origin, and then you have a upright parabola that you're used to. So these parametric equations give you sets of functions, and then we'll see what we can do with them, right? It's really, really cool stuff. For certain things, it's completely pointless to use parametric equations because there are absolutely zero benefits, right? But that's just, right? So y equals 3x plus 5. Completely pointless to make parametric equations for this because you are not achieving anything and you are making the matters worse now to have two equations instead of one where these two are completely the same equation, right? So pointless for some cases, but very useful for others. So it's situational. You don't get to use parametric equations all the time. However, in Calculus 3, you are forced to use parametric equations all the time. So actually you will be using this, even though it's completely pointless now to change this into parametric equations. Once you are integrating line integral over the linear line, the straight line segment, right? Then you will have to make up the parametric equations for that line segment and then use that in your calculation, because only parametric equations would work for it. But that's next semester, so you don't have to worry about that yet. What we want to learn is the way to graph parametric equations, and we are also going to find out another feature for them. So let's graph parametric equations. So say you have x equals t plus 1 and y equals t squared minus 2. Let's say this is your set of parametric equations. How would you graph this set? Well, you can use the middle school method of picking the points, calculating their values, and then just plotting the dots and connecting the dots. Just like in a coloring book, except you don't have to color. Right? So one step less. So what do? Well, now everything is driven by the parameter t, and we get to calculate both x and y, which will give us our ordered pairs, which we get to draw on a graph and go from there. So I'm going to start at t, which is time equals 0. You are going to think about a bug that is on the surface of the desk, and then this bug at t equals 0 is when the bug spawned. All right? So now you have t equals 0. So that's going to give me 1 and negative 2 as my x and y coordinates. So 1 and negative 2, that is the location for t equal to 0. and then t equals 1 second, you are going to get 2 and then negative 1. So 2 and negative 1, this location is for t equals 1 second. T equals 2 seconds is going to give me 3, and then 2 squared is 4, minus 2 is 2, so I'm going to get 3 and 2. And that's for t equals 2 seconds. For t equals 3 seconds, I'm going to have a 4, and then 9 minus 2 is 7. So this is 3, this is 4. 1, 2, 3, 4, 5, 6, 7 right here. And this is for my t equals 3. Let's try and see what we can do for 4. That's a 5. That's 16 minus 2 is 14. Yeah, we can squeeze that somehow. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, all the way up here. 4t equals to 4. As I said, once you have your dots, which you obtain by calculating x using x equation and y using y equation, we connect these dots using the solid line, and as you can see, it creates some kind of a half of a parabola. Are we expecting a parabola? Yeah, but we'll see that. I want to show one. Well, let's do the verify that it's parabola. So verify the graph by writing x goes t plus 1, from where t is x minus 1. Now plug that into the y equals t squared minus 2, which is, instead of t, I have x minus 1 squared minus 2, and that's equal to y equals x squared minus 2x plus 1 minus 2, y equal x squared minus 2x minus 1. There we go. So it is a parabola. And if you are to plug in negative 2 over here, if you are to plug in 1 over here, you better come up with negative 2. So plug in 1, you get 1, minus 2, minus 1. When these guys cancel, you get negative 2. So perfect. Very important feature of the graph, or parametric equations, which gives you a lot of points on the Calc 3 exams, is to realize that parametric equations have orientation. You see, if you have a two-dimensional xy graph, your two dimensions are x and y. But when you write them as a parametric set, you introduce also what we call parameter t, but you can regard that as a new variable. Well, that's going to bring an extra something to the table, because if x is still x and y is still y, t must bring something to the table. And what t brings to the table as a parameter, doesn't have to be t, could be s, could be whatever, it brings the orientation, meaning which way you get to move as the line develops, which is why I put t equals 0, 1, 2, 3, 4 on the graph. We see that this graph progresses up from 0 to 4. It will always progress in the direction of increasing parameter value. So, orientation of the graph is in the direction of increasing parameter value. Let's test that on our good old friend circle. X equals 3 cosine t, y equals 3 sine t. I draw the circle of radius 3 because we learned that the equation is r cosine and r sine. So r is 3. This is a set of parametric equations. They come bundled. You don't get to write one without the other, ever. And then in Calculus 3, you are going to add a z component to it. So you will have x, y, and z. That will be just another equation. And it's scalable, so you can work in any dimensional space with these. So if you want to develop something in 16 dimensions, go ahead. You will have 16 of these equations to deal with. So now going back to the circle, I can calculate at time equal t equals 0, where am I on the circle? Well, when t equals to 0, and we can actually do the good old xy. So when t equals to 0, x is 3 and sine is 0. For t equals pi over 2, t equals pi, and last t equals 3 pi over 2. So the first t equals 0 is this point here on x-axis. You see x is 3, y 0, so that's the point on y-axis. T of pi over 2, cosine of pi over 2 is 0, so that's a 0. And sine of pi over 2 is 1 times 3 is 3, so 0, 3. And we are here at t equals pi over 2, exactly what you expected. At pi, cosine is -1, so we get -3, and sine of pi is 0, so we get a big fat 0, and we are here at -3 for t equals pi. And finally, to finish the journey around, we have the cosine of 3 pi over 2, so cosine of any n pi over 2 is always 0, and the sine of 3 pi over 2 is going to be -3 over here in this case. So we are getting this point here, and that's t equals 3 pi over 2. Note that the increasing values for the time, now we chose pi's because the equations have sines and cosines. So we see that the orientation for the circle is counterclockwise. Maybe you want to write that in your notes. Default orientation for the circle is counterclockwise. Default orientation for the circle is counterclockwise. Default orientation for the circle is counterclockwise. So our clocks are backwards, right? They should be going the other way. But that's okay. Clocks are not as old as man. You know, the clocks are barely 400 years old. Something like that over there. These guys analog clocks with little hands. Before that, you had the sand. Look. That was it. You know when it trickles down? What are you gonna do? It's like the timer all the time, right? Just leave it on the timer. You can't go and say, oh yeah, it's 7:52. No. I have a little bit of sand left. That's it. Yeah. Exactly. Or to exploit it and be late. So we have the orientation business over here, and that's it. So guys, that's parametric equations. Right now we're going to take a look at the derivative, right? So we can find, and that stuff is cheap and easy. See, all of these are curves, right? And when you have a curve, you're going to have a tangent line, which means there has to be a derivative. And if you take the derivative, you get to calculate the tangent line, slope, and then the tangent line and all of that stuff. So let's take a look at the derivative of in parametric. Now, integration for parametric and all that stuff is in Calc3, so you don't worry about that. We only are going to take a look at the derivatives. And we are looking at dy dx. A very quick mathematical manipulation, which say dy dx, and what I do is I multiply by 1 over dt and 1 over dt. I know, cheap. So you get dy dt divided by dx dt. Believe it or not, that's the derivative. So if you are looking for the derivative, dy dx is just going to be dy dt divided by dx dt. That is the derivative. Where do you lose your grade? You lose your grade on the silliest possible thing. When I give you equations, x equals 3t squared minus t plus 1, and y equals, let's say, 2 ln t, which one goes on top? The bottom equation goes on top, right? So that's where, right? Because it's a dy dt divided by, so when you find your dx dt, you just need to remember that this one goes in the denominator. That's 6t minus 1, and this one is dy dt, and that's 2 over t. So when you are looking for the derivative over here, dy dx, you have to put 2 over t divided by 6t minus 1. So that's, that's the pitfall. Just make sure you are using appropriate function in the numerator and appropriate one in denominator. Now you get to fix this, 2 over t times 6t minus 1, and you have your derivative. Now, if the point is given to you, let's say tangent line at time 2 seconds, you will plug that in. So now slope is the derivative computed at 2 seconds. You can use the same notation like for integration. When you put that vertical line, instead of putting the limits, you just say compute at t equals to 2. So that's 2 divided by 2 times 6 times 2 minus 1. 2 is canceled, 1 over 11, and you have your slope. M equals 1 over 11. You have equation for x, you have equation for y. So x computed at 2, t equals 2, is going to be what? What do we have? 3t squared, so 3 times 2 squared minus 2 plus 1. And y of 2, well, this is going to be 4, 12, 10, 11. And the other one is 2 ln t, so 2 ln 2. So now your point is 11, 2 ln 2, y equal mx plus b. Hopefully you remember your calculus 1 tangent line. Y is 2 ln 2, m is 1 over 11, x is 11 plus b. These 11s cancel. B equals 2 ln 2 minus 1. You can make it fancy if you bring this 2 inside the ln, so make it ln 4 minus 1. But no one cares. So y is equal to x over 11. That's your 1 over 11 times x for m times x for slope times x. And then plus 2 ln 2 minus 1. And that is the tangent line. Tangent line at t equals 2 seconds. Whatever that curve is, when you draw that, and you can use that, you can use software to draw this. Once you have the graph at t equals to 2, you know that's the point 11 comma 2 ln 2. and you draw the tangent line at that point, which is a straight line like this. That's parametric equations. You are going to be sick of this. In Calc 3, you will do these parametric equations in 2D, which is the only one that I presented here. In Calc 3, you will add another equation for z to create a set of parametric equations for a linear line, which, and other things as well. But so it will look exactly the same as all of your equations you are used to. They all have that y equal mx plus b field. So these over here this is the line the only way to get the line in 3D is to write 3 parametric equations like this. And now obviously all of that will be explained in Calc 3, so you don't have to worry about that at all now. That's it on parametric equations. So they break dimensions into 2 or 3 or whatever amount of dimensions you have. They all use the common parameter, which is what binds them together. And you can use that parameter to combine equations and eliminate the parameter, eliminate parametric equations, and then just have the one equation. Usually those equations, if they require parametric, are not friendly, they're not functions. So parametric equations make our life easier. And then, because we are introducing a parameter t on top of everything that we already have as x and y and so on, that gives us an extra degree of freedom, which is, in this case, manifests itself as the orientation of the curve. So the orientation will be consistent with the way where the t increases its value. T doesn't have to start at 0, it can start at any value, but you have to have t squished between 2 numbers where one is smaller than the other one, right? One on the left is smaller than the one on the right. And to find the derivative, you will find each one of these independently in respect to t. You are using same rules from basic differentiation. Polynomials, it's just x to the n minus 1, or in this case t. And you can quickly come up and just make sure that when you are done with those basic derivatives, you plug them where they should go. The top is the y, which is the bottom equation, and the bottom is x, which is the top equation over there. And if you plug those correctly, simplify a little bit of algebra, everything should be fine. That's it. I hope you're not disappointed. Bye.